Welcome back to the second part of this section. We are looking at freezing point depression. Another consequence of dissolving a solute in a solvent is that the freezing point of the solution is lower than that of the pure solvent. For an ideal solution, the depression of the freezing point is given in an equation that's similar to that of the elevation of the boiling point. So we have delta T Fp is equal to Kfp times the molal of the solute, where the Kfp is the molal freezing point depression constant, and that's in degrees Celsius per molal. So degrees Celsius per molal times molal will cancel out those molals, telling us how much that freezing point will be depressed by. If you look at this example here, adding antifreeze to water prevents the water from freezing. So here's pure water, and there's water with antifreeze in it, and the freezing point has been lowered. Let's look at an example problem. What mass of ethylene glycol must be added to 5.5 kilograms of water to lower the freezing point of the water from 0 to negative 10 degrees Celsius? Well, we're told that we are lowering that freezing point by negative 10 degrees Celsius. If I look up the freezing point constant for ethylene glycol, it's negative 1.86 degrees Celsius per molal. So we need to find the molality. If I find molality, remember molality has units of moles per kilogram, moles of solute per kilogram of solution. So if I can find moles, I can find mass by using this molar mass. So if I find molality, I'm going to divide both sides by negative 1.86. That gives me a molality of 5.376 moles of ethylene glycol per kilogram of water. We're told that we had 5.5 kilograms of water, so that will cancel that unit out, leaving us with 29.57 moles of ethylene glycol. And I found the molar mass of ethylene glycol, so we went from moles to grams. With three significant figures, there would be 1,840 grams of ethylene glycol. Here's another one. In northern United States, summer cottages are usually closed up for the winter. When doing so, the owners winterize the plumbing by putting antifreeze in the toilet tanks, for example. Will adding 525 grams of antifreeze, or ethylene glycol, to 3 kilograms of water ensure that the water will not freeze at negative 25 degrees Celsius? Well, let's write down what we know. We can actually find the molality of this ethylene glycol because we're given grams of it. We can find that molar mass and go grams to moles. If I know moles of solute and kilograms of solvent, we're told that we had 3 kilograms of water, we can find the molality. If I know molality and I know the freezing point constant of water, I can find that freezing point depression. Multiply those two together and I got negative 5.24 degrees Celsius. Well, water normally freezes at 0. So with my freezing point depression at negative 5.24, that would be negative 5.24 degrees Celsius. That will not give you protection down to negative 25 degrees Celsius. So no, that would not work. Our next topic in this section is osmosis. Osmosis is the movement of solvent molecules through a semi-permeable membrane from a region of lower solute concentration to a region of higher solute concentration. A semi-permeable membrane is a membrane that is permeable to some substances but not all. It's usually a thin sheet of material like a vegetable tissue or cellophane, and water molecules can pass through the membrane, but larger, let's say sugar molecules or hydrated ions cannot. And again, here's our big point. In osmosis, the solvent can move through the membrane, and it's always moving from higher solvent concentration to lower solvent concentration. That solute cannot move through the membrane. The net movement of solvent is always toward the solution with the higher solute concentration. Over time, the level of sugar solution inside the tube rises, the level of pure water in the beaker falls, and the sugar solution becomes more dilute, and eventually no further net change occurs and equilibrium is reached. Let's look at this figure. Here in A, the bag attached to the tube contains a solution that's 5% sugar, 95% water. The beaker contains pure water. That bag is made of a material that is semi-permeable, meaning it allows water but not the sugar molecules to pass through. Over time, the water flows from the region of low solute concentration, which is the pure water that's in the beaker, to the region of higher solute concentration, which is the sugar solution inside of that bag. Flow continues until the pressure exerted by the column of solution in the tube above the water level in the beaker is great enough to result in equal rates of passage of water molecules in both directions. The height of the column of solution is a measure of osmotic pressure. And you can notice the difference. Here I have a partially deflated bag, and I've got my solute concentration is greater inside of the bag. And you can see that water flows from the region of low solute concentration, because there's none here, into the bag where it's higher solute concentration. Here's another example. We can look at an egg. A fresh egg is placed in dilute acetic acid, and the acid reacts with the calcium carbonate of the shell, but leaves the egg membrane intact. The egg's membrane serves as a semi-permeable membrane. Osmosis occurs in one direction if the concentration of solute is greater inside the egg than the exterior solution, and occurs in the other direction if the concentration of the solution is less than the exterior solution. So in both cases, the solvent flows from the region of low solute concentration to the region of high solute concentrations. So the first example, part B, it's placed in pure water. So the solute concentration is greater inside the egg. So the pure water enters the egg and the egg swells. But when it's placed in corn syrup, that means that the solute concentration is greater in the corn syrup. So the solvent flows out of the egg into the corn syrup and the egg shrivels. Let's look at the particulate level. From a molecular point of view, the semi-permeable membrane does not present a barrier to the movement of water molecules, so they move through the membrane in both directions. Over time, more water molecules pass through the membrane from the pure water side to the solution side than in the opposite direction. The net effect is that water molecules move from regions of low solute concentrations to region of high solute concentrations. And we can see those water molecules that are passing to and from, but not the solute molecules or the hydrated ions. Like we said earlier, equilibrium is reached when the internal pressure of the apparatus equals the external pressure of the open tube. That pressure that's created by the column of solution for the system at equilibrium is a measure of osmotic pressure. That is, the osmotic pressure is the difference between the height of the solution in the tube and the level of pure water in the beaker. We can then represent osmotic pressure in an equation. This equation looks very similar to ideal gas law, PV equals nRT, but this osmotic pressure takes the place of P pressure, and C is equivalent to moles divided by volume. If you think about it, C, moles divided by volume in liters, moles per liter, is molarity. That's concentration. Remember, temperature is always in Kelvin, and R is a constant, 0.08206 or 0.082057 you might have seen. So let's look at an example problem. We're told that polyvinyl alcohol is a water-soluble polymer with an average molar mass of 28,000 grams per mole. You dissolve 1.844 grams of this polymer in water to give 150 milliliters of the solution. What is the osmotic pressure measured in 27 degrees Celsius? So it's asking for osmotic pressure. I'm going to look at that osmotic pressure equation. Osmotic pressure is equal to the concentration times R times T. We're given T, 27 degrees Celsius. We can get it into Kelvin. We always know R, and we can find concentration in moles per liter. If I'm given grams and milliliters, let's get grams to moles and then divide it by 0.150 liters. So that's what I did using the molar mass given of 28,000 grams. That gave me this many moles divided by 0.15 liters. There's my concentration. That will get plugged into the concentration. There's my R. There's my T, 300 Kelvin. And I got an osmotic pressure of 0.011 atmospheres because remember my gas law constant is in liters, atmospheres, moles, Kelvin. So my pressure would be given in atmospheres. And if I want to get it into millimeters of mercury, I just need to do a dimensional analysis problem because there's 760 millimeters of mercury in 1 atmosphere. So I would take my atmospheres and times it by 760 to get this 8.2 millimeters of mercury. Let's look at another problem. We have bradykinin, which is a small peptide that lowers blood pressure by causing blood vessels to dilate. What is the osmotic pressure of a solution of this protein at 20 degrees Celsius if 0.033 grams of the peptide is dissolved in water to give 50 milliliters of solution? We need to find concentration, which is moles per liter. I started with my grams. I'm going to go to moles using the molar mass given, and then take my moles and divide it by the 50 milliliters, which is 0.05 liters. That gave me my concentration. I know my R, and I found my temperature, 20 plus 273 to get 293. And again, my osmotic pressure will be in atmospheres. Osmosis is of practical significance in medicine. Patients who become dehydrated through illness often need to be given water and nutrients intravenously. Water cannot simply be dripped into a patient's vein. The intravenous solution must have the same overall solute concentration as the patient's blood. The solution must be isoosmotic or isotonic, which is this middle picture here. If pure water was used, the inside of a blood cell would have a higher solute concentration, and water would flow into the cell, and that would cause a hypotonic solution. And your red blood cells would burst. See how they get inflated? The opposite situation, hypertonicity, occurs if the intravenous solution is more concentrated than the contents of the blood, which would be this guy. So to combat this, a dehydrated patient is rehydrated in the hospital with a sterile saline solution that is 0.16 molar sodium chloride, a solution that is isotonic with the cells in the body.